Hello students, welcome back. The next topic is the greatest common divisor, section 3. Here's the definition of the greatest common divisor, the GCD, and the least common multiple, the LCM, as we had been studying since elementary school days. Elementary school, maybe I'm exaggerating, but at least from middle school days we had been doing this. Let A and B be integers that are not both 0. Then we define the greatest common divisor of A and B as the largest integer that divides both A and B. We denote it as the GCD of A and B like this, or simply A comma B like this when there's no danger of confusion. Now what if A and B are both 0? In that case, we can define the GCD as 0. That's standard. But not everybody agrees. Some people skip this altogether and do not consider 0 case at all, like our textbook author. Me, on the other hand, I'd like to keep it. So either way it works out, so it's not that big a deal. What is a big deal then? This one right here, which I'm highlighting in bold right now. The largest integer that divides both A and B always exists uniquely. We must prove that. And after that, and only after that, we can properly define the greatest common divisor. Consider, you're trying to define something, but that something may not exist. Well, nothing will make sense. So we have to prove this in order to have a well-defined concept of greatest common divisor. We're going to do the same thing for the least common multiple. Let A and B be non-zero integers. Then the smallest positive integer that is divisible by both A and B always exists uniquely. We're going to prove that. And after that, and only after that, we can properly define the least common multiple. We're going to define the least common multiple as that number that always exists uniquely, and we're going to denote it like this: the LCM of A and B, or simply A comma B with bracket when there's no danger of confusion. But even when there's no danger of confusion, I'll try not to use this one or that one. Whenever possible, I'll use GCD and LCM like this. And there are some exceptions, of course. We may have to consider GCD of GCD of GCD of something, and writing the GCD many times is too cumbersome. In that case, I may do some abbreviation. Same goes here, but those are going to be rare. I'll try not to use those. And finally, the trivial case for LCM, when one of them is 0, yeah, let's not consider those. Okay, all right. Now, we're down to the theorem that two theorems rather, that the largest integer that divides both A and B always exists uniquely, and the other version down here, blue and green. Blue first, GCD first. Let's begin the proof. Let's S be the set of all common divisors of A and B, like this. What we want is the maximum of the set. So we have to prove that the maximum exists. And if it exists, then of course it exists uniquely, because if there are two maxima, then they're both greater than or equal to each other, so they're the same. The detail is left to the student. Now, what property am I going to use? Well, Z is discrete and totally ordered. So it is well ordered in both directions whenever bounded. Z itself is not well ordered, but if it is bounded, then yes. If it is bounded below, then it is well ordered in forward direction. Every non-empty subset has the smallest element, the minimum. If it is bounded above, then it's the opposite. It is well ordered in backward order, so every non-empty subset has the largest element, the maximum. In this case, we have to prove the latter. So we have to prove that the set is non-empty and bounded above. Now the empty part is going to be a bit easier. Can you think of a number that divides both A and B? There gotta be one. At least two of them, actually. Well, here's one. 1 divides every number. So does -1, but 1 is easier. So 1 belongs to S, so S is non-empty. Okay, alright, 1 down, 1 more to go. How about bounded above? That's a bit trickier. We can consider this kind of argument. So select any C from S. So it's a common divisor, alright? C divides A and C divides B. Therefore, C is less than or equal to A. Well, not really. A could be negative, so let's make it absolute value. And C is less than or equal to absolute value of B, like this. Therefore, C is less than or equal to the minimum of the two. Smaller of the two. How's that? So this minimum of these two, smaller of the two, is an upper bound. It's greater than or equal to all C in here. So if this is bounded above, so there gotta be a maximum. All good? Everybody agrees? No, something is wrong. Find out. Stop the playback and find out what is wrong with this attempted proof. Okay, time's up. When does it break up? It breaks down if A is 0 or B is 0. If A is 0, as I'm highlighting in purple, then this may not hold. You know, every number divides 0, but that doesn't mean that number is less than 0. 100 times 0 is 0, so 100 divides 0, but 100 is not less than 0. And then the same goes for B equals 0, as I'm highlighting in brown. So this doesn't work. When A and B are both non-zero, it works out, but if any one of them is allowed to be 0, then it doesn't work anymore. But it is possible to make it right, as a matter of fact. It's a bit messy, but we can do it like this. This may not work, but this works out. Changes and into or, and then it works out. Why is that? Well, if both A and B are non-zero, then yeah, both of these work. So C is less than both of those. So less than the minimum. Less than or equal to the minimum at the very least. Now, if A is 0, then this will not work, but this will work. If B is 0, then this will fail, but this will work. Either one of them has to work because not both of them are 0. One of them is non-zero, so either this one works or that one works. Or maybe both. If both are non-zero, that's this case. So instead of the minimum, we have the maximum. And that completes the proof, but there's a bit of a problem with this proof as well. We need some lengthy explanation. We need some lengthy explanation. So how would you explain those? Cut those off to A and B are both non-zero, A is 0, B is non-zero, B is 0, A is non-zero, like that, and A, B are both 0, that's impossible. You can do things like those. Yeah, okay, given time and space, you can write all those down, and I'm going to leave those to you. It works. You can make it work. I'm going to leave that to you. But here in this notebook, I decided to use a little simpler and more elegant method. This is what I did. Select C from this S, so C is a common divisor, so C divides A and C divides B. Therefore, C divides absolute value of A and absolute value of B. You see, C times some integer is A, and A same as absolute value of A, then no problem, but if it is not, then multiply -1 again, then we're going to get this. Same for this. So we get that. And then if you add them up, C divides some of those absolute values. Now, because C divides that, we can say C is less than or equal to the absolute value of A plus absolute value of B. Now it works because not both of them are 0. This is non-zero. That's positive. You see? Not both of them have 0. One of them is non-zero. So this thing is positive, so it works out. Yes, you can make it into a one-line proof like this. As a result, S is bounded above and non-empty, so the maximum exists, and that maximum is the greatest common divisor. Now we have another comment here, another version here, and this is the GCD for n numbers, A1, A2, A3, all the way up to AN. Again, you can prove that the largest integer that divides all those AIs always exists uniquely, and that proof is left to the students. Actually, it's right here in proof 2, but I'm not going to open it. I'm going to leave that to you. Next, let's go to LCM. This one is actually easier. And by the way, we can consider the n number version as well. A1, A2, A3 to AN, and then we can find the smallest non-negative integer that is divisible by all the AIs, and that number exists uniquely all the time, and that's the LCM. You can do that, and that extension is again left to the students, and actually it's in proof 2. As for the proof of the standard case, it's actually a bit easier. Let S be the set of all positive common multiples, and we're going to find the minimum of this, right? Now this is coming from the set of all positive integers, which is well defined. So all we have to do is to prove this is non-empty. And it is non-empty because we can find at least one element, absolute value of A times B. A divides A times B, and B also divides A times B, but that A times B could be negative. So if so, then extra -1 is multiplied so that we get absolute value, then it works out. And absolute value of A times B belongs to this S, yes, because A and B are both non-zero. So we have a non-empty subset, so it has a minimum, and that minimum is the least common multiple. So that completes the setup, the GCD and LCM.